In this presentation, our group will describe the paper, The Vehicle Scheduling Problem for Fleets with Alternative Fuel Vehicles. We will introduce the background of the problem, 3 algorithms used in paper, how to improve the solution technique, and where we are going to get data. Scheduling fleets of vehicles is an important aspect of designing many logistic systems. For environmental sustainability or government regulation reasons, a fleet of vehicle is changed to a fleet of alternative fuel vehicle. This paper mainly modeled the alternative fuel multiple depot vehicle scheduling problem and modification of the normal VSP problem. This problem can show in this picture. It is an example of AFVSP problem. The arrow means service trip, and the dotted line means dead-handing trip. It means, given a set of unserviced trips with cost and times assigned for vehicle to travel from the end location of one service trip to the start location of another. The circle means trip start or end point. The triangle means fuel station. The square means depot. 3 algorithms are the column generation algorithm, the branch and price algorithm, the heuristic algorithm for AFVSP. The column generation algorithm. The problem is firstly formulated as a binary integer programming problem. The binary integer program will then be relaxed and solved using column generation. Column generation divided problem into a restricted master problem and a subproblem. In the column generation algorithm, first generate a graph G corresponding to the problem. Make a formulation based on the graph, which represents all possible ways of visiting a fuel station following a service trip or a depot. Use constraint ensure all the situation. Use label correcting algorithm on subproblem. The label correcting algorithm is used to help find the new best solution. There are some advantages for this problem. First, no longer have to consider the time component of the service trip. Time is fully captured by the location of arc in the graph G. Each service trip is associated with a single vertex. So, the different start and end location of each service trip are amounted for in the arcs. Every cycle in graph G corresponds to a schedule that could be taken by a vehicle. The disadvantages in this algorithm is the number of flexible schedule is intractable for problems with all but the smallest number of service trips, and thus it would not be possible to even generate in integer gram.
Hi everyone, I'm the second presenter of the project because we are all in different places. So we separate the presentation into 3 pieces and we'll combine them after all of us have done. The answer done the project based on MATLAB, whereas we will remake it on Groovy Python. The Groovy Python would solve it by using branch and price algorithm automatically. And what we can do would just apply some optimizations. The paper also mentions that they also involved branch and bound algorithm to put a limit on the solver to accelerate the calculation. Generally, when the result is not integer, outputted by the column generation algorithm. So that's why the branch and price approach is used. Branch and bound algorithm also are a class of algorithms that find an integer solution to a problem by repeatedly solving linear relaxations of the problem. We and the solution to the linear relaxation is not integer, then the problem branches into multiple subproblems that are also linear relaxations. We start by storing an upbound of infinity for the solution. When a new integer solution is found, if it has a cost lower than the current best cost, then it is stored as a new best solution, and its cost is used as a new upbound. When a non-integer solution is generated, if the relaxed cost is greater than the current upbound and the problem is prolonged, if the non-integer solution has a relaxed cost less than the current best upbound, the problem branches into two new problems. This continues until all of the branches have either ended in integer solutions or have been prolonged since their low bound is too high. We would just reuse the outcome of the formal calculation rather than rather than calculate from the initial problem. So that's also the core ideas to accelerate the calculation process. And now the paper also discussed about a heuristic algorithm for AFDSP problem. Since the problem is NP hard, the column generation would be time consuming to run. Those heuristic algorithm, one that's designed to solve a problem in a fast and more efficient fashion than traditional methods by sacrificing optimality, accuracy, precision, or completeness for speed is used. The core idea of the heuristic algorithm is to calculate a good solution rather than the best solution, which could take much more time. Assign the first service trip T1 to vehicle 1 to vehicle V1 for each depot with available vehicles. Use the FSA to determine at which stations to refuel. For the depot with the minimum cost assignment, assign the vehicle to that depot. Set I equals 2. That's just the basic idea of the heuristic algorithm that the paper has mentioned. It is based on the previous research papers, so to calculate the good solution. And we can see, and you can see from the back of the paper, there is a table there is a table lines some research data, and you can see the outcome could be solved as a very short time, maybe 2 or 3 seconds. And in the heuristic algorithm, the concurrent schedule algorithm is also mentioned. It was used by the formal. It was also mentioned by the formal research papers.
Now it comes to the problem that what do we have to improve the solution techniques? So we respect the great work done by Jonathan and Pitu. They developed several algorithms to address the vehicle scheduling problem in a fast and accurate way. I think our job is firstly to build our own model to solve the problem. Then we can add some sort of heuristic algorithms like primal heuristic to have a faster computation speed in GROB. Another way is using Bender's decomposition to fit the bench and price algorithm, because as we all know, that is used to solve mixed integral programming problems. Bender's decomposition has been successfully applied to take advantage of underlying problems structures for various optimizing problems. Finally, here comes one of the most important parts of our projects, which is where can we get the data? Just like Jonathan and Pitu did in their paper, we are going to get the data in 2 ways. First is to randomly generating data, and the second is directly getting the data from Valley Metro Bus Network in Phoenix, Arizona. So the first way is random generate data. We found that the data was generated by former researchers' model, and there's a little change was made to fit the situation. We need to restrict the range of data. such as the distance between the start point and end point, so that they may not need to refute so many times in the model. Since our group are not majored in the transportation industry, the data is generated based on the real database. Talking about the real database, we found the data from the Valley Metro Station on a website called Valley Metro Open Data Geocenter. This website provides datasets about bus stops and the routes. Here is the screenshot for the routes data on the website, and this is the visualization of the routes. But there are two problems. First, the warehouse and the fuel station data are not available on the GeoCenter. That is to say, we lack two sets of data for the problem. Secondly, the author used data from the city of Phoenix in 2013, and we can only access to those datasets in 2019. So there, our dataset might be different from the author's dataset. So in order to address the two problems, we have emailed the authors and asked them for the data they have used in their paper. Moreover, we can use transportation data from other cities to simulate the problem. For example, the Queensland government provides General Transit Fuel Specification, which defines a common format for public transport schedules and associates geographic information. That's all. Thanks for watching.